It's time now to move on to the presentation by Mike Martynowycz, who's a postdoc at UCLA and the Howard Hughes Medical Institute, working with Tamir Gonen. And his presentation is going to be Cryo-FIB milling improves MicoED data and structures.
Thank you very much, Steve, for the invitation and the opportunity to share my work with you. Hoping you can see my slides and hear me. That would be great. Okay. So thank you again. And I'm Mike Martynowycz. I'm a postdoc in the Gonen lab, and I'm going to be talking to you guys today about cryo-FIB milling of membrane protein structures and some MicoED work we're doing in the lab. And I kind of want to start it right off with what is MicoED? And MicoED is a cryo-EM method known as microcrystal electron diffraction. It is a cryo-EM method where the idea is you apply a slurry of microcrystals to an EM grid. You blot away the excess material, the excess water. You vitrify these crystals just like you would an EM grid. You load this EM grid into a cryogenically cooled transmission electron microscope. You locate a crystal, which you bring to the eccentric position, and then you expose the crystal to a parallel electron beam. This parallel electron beam, while this is happening, you continuously rotate the crystal in the beam and read out the diffracted intensities, very analogous to the rotation method in X-ray crystallography. You could look back at the movie you've collected and plot out where all of the spots are and where they should be. And from this information, you can determine the unit cell and the symmetry of the crystal. So you could imagine that each one of these frames contains some small fraction of the three-dimensional reciprocal space. And in this three-dimensional representation, you can take all of those intensities and essentially take the square root of them and combine them with the crystallographic phases to produce a map. And in this way, we create a map using exposures of only about 1 electron per angstrom squared total in the TEM. For the crystallographers, this roughly correlates to 4 to 5 megagrays of dose. And at these types of doses, we can build models that show completely intact disulfide bonds and completely resolved acidic side chains for the most part. The whole reason we build these models into these maps is to find out what the structure of the protein is. And this goes back to this wonderful central hypothesis of structural biology being, if you can tell me where all the atoms are of a molecule or what it looks like, I can tell you what it does. This is the structure function relationship. So in this way, which is more or less a standard approach to cryo-EM, we've been able to solve many protein structures. You can think of this as a standard EM method where you just put your microcrystals on a holy carbon or lacy carbon grid. You do your standard blotting and hope for the best. In most cases, you don't have tiny little microcrystals that are perfect. A lot of times you might have crystals that have, they're clumped together, or they're bunches of needles, or they're just bigger crystals that you want to try and make smaller. In these situations, you can sonicate the crystals, or just grab your pipetters and do the Yvonne Drago and crush your crystals with a pipettamen. We've been very successful with this in solving structures using sonication or pipette disruption. And over the years, we've solved more and more soluble protein structures, natural products, now small molecules, protein-protein complexes, and even membrane proteins. There are something like 20 labs in the world that are now doing MicoED, and every year it's getting bigger and bigger. But we didn't unveil MicoED for solving normal protein structures. The whole idea was these guys, was looking at these membrane proteins. The reason being is membrane protein crystals often grow really, really, really tiny. So the first membrane protein structure that our lab attempted was NAC, which is the non-selective cation channel. And this was solved by X-ray. And Xianlu was able to grow giant crystals of NAC, which you could use for X-ray. And we noticed that when you tried to sonicate them or disrupt them, they would just completely dissolve. In fact, most membrane protein crystals don't like being touched at all or disrupted in any way. They just melt. So after a long time, Xian was actually able to make sparse screens where he could make drops that looked like this with tiny little tiny granular looking crystals that fluoresced in UV. And after putting them on the grid and screening around, he was able to find, these tiny little cubes. This cube, for example, is about 700 nanometers by 700 nanometers. And from these tiny crystals, he was able to solve a 2.5 angstrom structure of NAC, where he was able to see the coordinated sodium ions all the way down the 4-fold axis in a new form of solvation right at the gating center of the protein, which made us learn something new. But the problem was, if we can't disrupt a whole bunch of crystals, there's a whole bunch where you can't just go in and blot, or you can't sonicate, you'll destroy them. In these cases, we would just gently blot the grids and put them in the TEM, and almost always they would look like this. With that one on the right there is the thing of nightmares. And we spent a lot of time looking around the thinner areas of these crystals or grids, trying to find crystalline edges and things. But this is a horribly inefficient way of trying to find these tiny crystals. So we were inspired by the work of Mike Marco and the tomography community, where they were able to use a scanning electron microscope on a focused ion beam to look at their grids and then make them into samples usable for tomography. So we thought, hey, let's try taking a look at some of our crystals and see if this works. And to our surprise, we took one of those grids that looked like all black. We couldn't see a thing. And from the scanning electron beam, we saw something that ended up looking like this, which is super promising. We liked all that. And if you zoom in, you can actually see that, our crystals are kind of like tortellini in a colander being blotted and just sucked into where these little holes are and clumped together. But this was the problem where these crystals were too big for MicoED. You can only have about a micron thick in your TEM. And these were, 10 to 5 microns, which still made them a pain for X-ray diffraction. So what do we do in this case is we find a crystal and we align it in the electron beam and the ion beam. And in the ion beam, we can just draw these wonderful rectangles and kindly ask all of the material in them to leave. And in this way, we can thin the crystals progressively and keep an eye on it in the electron beam as we go and make them thinner and thinner and thinner until eventually we are left with just a very thin plank of crystalline material, only 200 to 300 nanometers thick. We can transfer these lamella, is what we call them, into a cryogenically cooled transmission electron microscope, take an all-grid atlas from those dark grids we saw before, and we will see these wonderful thin strips of white material, of white, with a tiny little piece hovering on it of the lamella we've made. So we can put on our CSI hats and zoom and enhance on what we've done here. And we can keep looking closer and closer. And eventually you'll see that we have a crystal embedded in liquid where you can see the separation between the liquid and the crystal. We can use a selected area aperture to select only a small area of the crystal and lamella, and then collect a continuous rotation MicoED data set of up to 140 degrees continuous rotation. So this is, of course, lysozyme, which is the lysozyme of lysozymes, and it solves no problem. We got a beautiful structure out of it. So this method is actually super useful and better than what we had been doing, in my opinion, at least, where in the past, if you look at the Tatna et al. Paper, what we'd done is we hunted and pecked around a grid of sonicated crystals. Each crystal we'd collect 12 to 24 degrees from, and we'd play around trying to merge them until we got a complete data set. For now, what we can do is we can take one lamella, collect 60 to 90 degrees. This is one data set on the left. We can get better statistics, and these intensities are much better in that right after molecular replacement, you get maps that look like this, with holes in all of your tryptophans, and everything is quite good. So we were reasonably certain that this method works. But does it work for the membrane proteins we care about? So we were working on the murine voltage dependent anion channel, or MVDAC, murine being mouse, which crystals are grown in bicells. This is just a fancy way of taking phospholipid and chapso. You combine it with your solubilized protein to make this wonderful little protein complex. And according to the literature for VDAC, you get these beautiful crystals. The problem was our MVDAC was a mutant, and the crystals we got looked like this, which looks like someone sneezed into our crystal tray. If you take these and put them on the TEM grid, you get all black, you see nothing. After that, we were like, well, let's look at it in the scanning electron beam. And yes, often we'd see things that were just absolutely terrible. We can't do anything with this. We can't do anything with this. And after some optimization of drops that looked like this, we eventually got grids like on the bottom right here, where they were thin enough to where we could possibly see something. And after that, one day I was looking really close with the ion beam at these grids, and I was playing a little bit of Where's Waldo, and I went, aha, a crystal. I don't know if you can see it. I'll give you a second, but that's where I ended up milling. And when you look at this at a little different angle, it turns out that yes, it's a crystal, and yes, it's in a super deep, dense lipid matrix. Putting this into the TEM, what we saw was about a 3.2 angstrom structure of the mutant VDAC, where we were able to solve it by molecular replacement, see the mutation, kind of what we expected in terms of the structure. But what we saw that we didn't expect was in the crystallographic map in between the protein subunits were lipid densities that were just not quite resolved enough because of the resolution of how the lipids are packing with these proteins. We were really excited about this and started working on other membrane proteins that were embedded in dense media, like lipidic cubic phase. And 1 month after, Mike. Yep. Okay, so 1 month after this, we were able to solve the human adenosine receptor in LCP, which my colleague will talk about tomorrow. And I want to plug all of the great MicoED talks that will be happening tomorrow and in the coming weeks. Thank all of my lab members and of course, all of the people who paid for this.
Thank you very much, Mike. Great talk. Please put any questions for Mike in the chat. And so Mike, let me exercise the chair's prerogative. You mentioned that I think you mentioned that all these structures are being determined by molecular replacement, and pre-AlphaFold. Of course, that might have been a criticism leveled at the technology, but I think that concern may have considerably diminished as a consequence of the successes of AlphaFold 2, of Rosetta Fold, in terms of predicting structures at least of accuracy sufficient for doing MR. Do you have any experience with cases where you've taken predicted structures to use for MR?
So internally, we're playing with this now. Just like everybody else, we're having a lot of fun looking at all of our data and all of the things we can do with AlphaFold or Rosetta Fold and the predictions. Before that, there were also homology servers that were pretty good, not as good though. Mm-hmm. And internally, we are also looking always at the idea of experimental phasing and new approaches to getting to solving these structures.
Thank you. Let me cut off that answer and ask on behalf of Ethan Cartagena, what advantages do you think that MicoED has over traditional X-ray crystallography?
The biggest one being the stronger interaction between electrons and matter than X-rays and matter. So we can use crystals that are
minuscule, literally. Yeah, literally minuscule. And then Lisa Katorcha from Anatrace asks, Mike, which lipids did you use for the MVDAC crystallization structure prior to LCP?
So for MVDAC, this was in DMPC and cholesterol in a mixture.
and you could nearly resolve those, but not quite.
Yeah, we're hoping to actually push that a little bit in the future, because seeing, a resolved lipid shell would be pretty exciting.
Terrific. Well, I ask you to thank Mike and Cynthia for a great start to this session. And with your reactions, you can provide applause, you can do thumbs up. Thank you very much. Great talks from both of you. We have a 20-minute, please be back at 1:20 p.m. sharp, coffee break. And at that point, my co-organizer, Dr. Natalie Stranadka from the University of British Columbia, will be chairing the remainder of the afternoon session. And then at 3 p.m., there'll be an opportunity for the speakers to discuss in a panel and reflect on what they've told us and the implications for the next 50 years of the protein data banks. So thank you. We're off to a great start.